So this is a quick review of what's going to be on your summative number 4. This first section is on advanced factoring. This is the third time we've tested advanced factoring, so I can say with pretty severe certainty that this is the last time I'm going to be testing this section. So make sure you capitalize on the fact that you're getting a retake. The first two questions are similar in nature because they are both the cubic patterns. So remember, you're using your green factoring flowchart when you're doing this question. I'm going to do 1b. So for 1b, 64x to the third minus 125. How about I do all the b's, or at least the second problems of everything here? I think in class, whichever co-teacher we have for that class is probably doing all the a's, so this will give you an opportunity to get all the questions done with a little teacher help if you need it. Alright, so we have the difference of two cubic numbers here. Right now we have a to the third minus b to the third. So in order to use the pattern, which is a minus b times a squared plus ab plus b squared, we have to know who a and b are. So this number and this number need to be cube rooted. So remember, we're cube rooting 64x to the third, and that's going to give us 4x. And then similarly here, we're cube rooting 125, not the negative, just the 125. But we're going to get 5 for b. So filling in our pattern, a minus b would be 4x minus 5. And then a squared, this is where some kids mess up because it's 4x times another 4x, so that's 16x to the second. Gosh, it's Monday and my handwriting's not so great. Alright, plus a times b. If I were to multiply these two numbers together, I'd get plus 20x. And then plus b squared, 5 times 5 would be plus 25. So that says 4x minus 5 times 16x squared plus 20x plus 25. The next factoring pattern we need to be aware of is, this one gave a lot of trouble on the last summative, right? Let's do 2b together. So at the top of the flowchart says look for any common factors. In this case we do have a common factor of a 3. So we're going to take out the 3, and you still have x to the fourth minus 1. Now inside these parentheses, x to the fourth minus 1, that is a difference of two squares pattern, which factors into our good twin, evil twin factoring pattern. The 3 is still out in front though. So we have x squared plus 1, and then we have x squared minus 1. And on the last summative, a lot of you stopped here, and I had to write you a little message about keep going. X squared minus 1 is still the difference of two squares. So that factors further into x plus 1 times x minus 1. But the sum of squares does not factor further, so leave that as x squared plus 1, and then of course leave that 3 out in front. So don't be surprised when you see a question that involves multiple layers of factoring like that one did. 3 layers to be exact. And then our favorite factor by grouping. So I'll do 3b. Common factor here of 5x squared. And if you factor out a 5x squared from each term, you still have an x minus 3. And remember, your parentheses should match when you're done, so keep that in mind when you decide what to factor out of this next group. What if you factored out a negative 1? Because that would change everybody's sign, so that would turn this to a positive x and a negative 3, which is what I need. Awesome. So now, in the entire problem, you'll notice that each term here, this is a term and this is a term, there's an x minus 3. So you need to factor out that x minus 3, which removes it from the original problem. And then all you have left is a 5x squared minus 1, grouped together, of course. And I'm always paranoid about further factoring, but these are not the difference of two squares, because square root of 5 is gross, so we're just going to leave that as that answer. Alright, so this is our first chance at testing out the fundamental theorem of algebra. I'm hoping not to have to test this one again, guys, so let's make it count. How do you determine how many solutions a polynomial has? Well, that's actually the whole point of the fundamental theorem of algebra. It's whatever the degree is. So the degree equals the number of solutions. Now, notice I didn't say like unique or real or imaginary, just whatever the degree is, the highest exponent, that's how many solutions you're going to be finding. So write an example of a polynomial of 4 solutions. There's a lot of different things you could write down, guys, but the idea is it's got to have x to the fourth and then plus whatever can follow it. So, like x to the fourth is actually a good answer. So I think the way the question's going to be worded for you is how many solutions does this polynomial have? So you have to know to look for the degree, and then that'll be your answer. Alright, so here. we need to use our graphing calculator, and I tried to really walk you through this question, guys. Use your calculator to find all rational zeros. So we're going to type this into our calculator, and we're going to find the zero from the calculator. I'm going to pause the video. You pause yours as well and get this typed in. Okay, I'm back for a brief moment. Wah wah. Didn't I say I was doing B's? So type that one into your calculator. Okay, sorry about that. So now we have the B version of the question typed into our calculator. I'm going to graph, and I'm going to look for any what we call rational zeros, which would be any place where the function crosses the x-axis that I could easily tell with my eyes. And I'm seeing -1, 2, 3, 4, -5. Seems like a good rational zero to use for my calculator. So from the calculator, -5. You can write that as an ordered pair if you'd prefer, but the idea is that goes into the box for synthetic division. And then we line up our coefficients for synthetic division, which is a 1, 5, 4, and 20. There's no missing terms this time. And then we go through the act of synthetically dividing, which we're really substituting, but that's okay. -5, this adds up to 0. 0 times anything is 0. That's a 4, and that's a -20. Remember, when you do fundamental theorem, and you're plugging in a 0 of the polynomial, your remainder should always come out to 0, and if it doesn't, then you messed up. So what we have is, these are the coefficients to a lower degree polynomial. We just cut it down by one level, so this is a quadratic. So 1x squared plus 0x's plus 4, which I'm going to write as 1x squared, I'm not going to write 0x's, plus 4. And I need to find my, notice here, imaginary solution. So that was a really gigantic hint to you that you're going to get I's in your next two answers. And remember, the degree tells you how many answers you're going to get. We just got 1 from the calculator, and we're about to get 2 more. So if I subtract 4, x squared equals -4, and then square rooting both sides here. -4, we're going to break into something like this, 4 times -1, and we're going to remember that this is 2i, but since we square rooted an equation, it's plus and minus 2i. That would be a good set of answers. 1, 2, 3 answers. Perfect. Alright. Now, more typing on the calculator. I'm going to do 6b with you. You probably already have 6a done from class. And I want you to pause the video. I'm going to pause, and we're going to get the function typed in. So I have 5b typed into my calculator, and in the standard viewing window I'm going to have a bit of a problem simply because I think there's a little maximum point that I can't see. So what I'm going to do is I'm going to extend my y maximum so my window goes up a little more. So instead of 10, let's go like 20 just to be safe. And then the first thing on the page that they want you to do is they want you to find any x-intercepts. Well, this one actually is very fortunate. There's only one x-intercept you have to find. This guy right here. So I can tell from estimation that it's around 4. So when I go to submit answers that are to the left and to the right of 4, I'm just going to think about numbers that are slightly smaller and slightly larger than 4. So going to the calc menu, you have to remember that 0 is the command to find x-intercepts, because those are the zeros of your function. And then it says left bound. I'm just going to remember my thing is a delay. So I'm going to make mine hop to like here, which would be at x equals 3. So I'm going to type 3, enter. You guys could scroll, obviously. And then right bound, I'm going to go like 5, which will drag it down there. Close enough. And then I noticed that my intercept is in between those two blue vertical lines that popped up. So enter one more time for guess. And I need to round to the 10th place. So 4.057 would round to 4.1. That's what I write down on my paper. That is not my paper. There we go. I already forgot. It was 4.1, wasn't it? And on your test, I wrote down as many parenthesis sets as you need. So if there's 3 x-intercepts, I put down 3 parenthesis sets. Remember, on your calculator, sometimes there's a pixelation issue, and you get something like 2.467e -20. Well, that's just scientific notation for 0. It's pixels creating a calculus problem, essentially. It's trying to do the most exact thing it can. So anytime this e shows up with a negative exponent, just remember that that means 0. Alright, max and min. There's one of each on this graph. So it doesn't really matter who you find first, but I'm going to find the maximum first because I feel like it. So this time, when you go to the command menu, you need to choose the correct one. So if I'm going to find maximum first, I'm going to choose maximum. Or not. I'm going to choose maximum, which is 4. And then when it says left bound, right bound, they're referring to of this maximum. So something to the left of that maximum would be like x equals 2, and something to the right of the maximum would be like x equals 4. So left bound, I'm going to go 2, right bound 4, and you guys can scroll again, as long as those two blue vertical lines pop up and it's in the middle. So once it says guess, hit enter one more time, and I want the entire ordered pair written and also rounded to the tenths position. So this would be 2.5, comma 11.9. Make sure you're careful on your rounding. Ugh. I already forgot what it was. 2.5, 11.9. And that was our max. 2.5, 11.9. So we're going to do those same steps to find the minimum, except we're going to need to pull up the right command. So, calc menu. This time, choose the minimum command, which is 3. And then when I go left bound, right bound of the minimum, I'm referring to this guy right here. So something to the left of him would be like at -1, and something to the right of him would be at 1. So that's where I'm going to go. -1 to the left. Oh, I typed the wrong thing. I typed a subtraction symbol. It doesn't like that. Here, -1. There we go. Enter. And then right bound 1. It's in the middle, so hit enter for guess. And then again, round to the tenths position. No more, no less, please. So 0.1, comma 4.9. If you estimate and you tell me that's at 0, I am not going to be happy with that answer, and I'm not going to accept it. I already forgot what it was. It was 0.1, 4.9. Alright, and then we got to get all this plotted. Yes. So, let's see, 4.1 is our intercept, and then 2.5, oh, that's going to be off the graph. That's okay, though. And then 0.1, 4.9 is roughly right there. So, oh my gosh, it's going to look really ugly because I'm graphing it. Okay, that was supposed to look better. Pretend. And actually, when you guys are graphing this, remember how I used to leave the arrows off? I'm going to do that again, because it's a little easier for me to tell where it's increasing and decreasing without the arrows. So this is where I used to grab 2 markers and color the parts of the roller coaster track that are increasing and decreasing. So for increasing, I use green, and this is where it's increasing, and that's the only time it's increasing. Every other part of the roller coaster, it's decreasing. So the important part here is you're going to give me a domain interval. So the question is, when does it change from increasing to decreasing? So I need you to give me the when that are associated with these 2 ordered pairs. And you already have that. They are the x values of your turning points. So one of them is 2.5 and one of them is 0.1. Take a wild guess, right? This is 0.1 and this is 2.5. So make sure you're giving me, these are domain intervals. So you should only be giving me x values. So it is increasing from 0.1 to 2.5. And it is decreasing. This is the weird one. It starts at -infinity, kind of, sort of, and then it stops decreasing at 0.1, but then it picks up again with its decreasing interval at 2.5 to infinity. And then now I'm going to put the arrows back on because they will help me with my end behavior. So end behavior, remember, x goes to the left and x goes to the right is always going to be there for our end behaviors. But this end behavior, because of the way I set it up, that is the left behavior. Look at the left side. It's going up, 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 up. So the function is going to infinity. And then the right side, which is this one, is going down, 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 down. So -infinity. All right. One more new topic that we tested, but it's a big one, right? So I'm going to do 7b with you, because I think your other teacher did 7a with you in the classroom. We're going to want to get this typed into our calculator. I'm going to pause the video. You pause as well. Alright, so get your function typed in. If you're on a newer calculator, you just got to make sure the x minus 2 is up in the exponent position. If you're on an older calculator, make sure the x minus 2 has parentheses around it and that you close the function after the minus 2. Also make sure that's a subtract 2 and not a negative 2. Alright, so graphing, clearly an exponential growth, which I'm sure is one of the questions. We already knew that though because the base was a 2, which is greater than 1. We'll get back to that idea in a moment. I'm going to steal some points off my table. And I don't need you guys to go crazy with points, you know. One of the major things, though, I am going to be looking for is that you recognize that the asymptote is now at a +4. So I would love it if everyone could get in the habit of highlighting somehow the invisible fence of the asymptote. And that way when you go to connect your points, if you're a sloppy grapher like me, you at least have a visual boundary, right? So graph a few points. Let's see. Alright, so I'm sure you'll do a better job than I'm about to do. Oh, man. Okay, so you actually have nice plotting ability. I don't. This is definitely growth. The horizontal asymptote we just saw was at the vertical shift of +4, so it's now the line y equals 4. I want to see an equation, please. The domain for all exponentials are negative infinity to infinity. And the range, remember, low to high, so it starts here, and then it measures upwards, right? Let me write sideways with my tablet. Alright, so the range starts at y value -4, doesn't hit -4 though, because it's not -4, there's a +4, and then goes up to infinity. But it doesn't hit 4 because of the asymptote line. It's not going to reach it. And then the weird one, end behavior, still starts off the same way where we fill in the x's for left and right end behavior. But if I look on the left side of my curve, the function is approaching the asymptote, which is at 4. And then on the right side of my curve, the function is going up. So one thing I'm going to check for when I'm grading this is that your horizontal asymptote, some part of your range, and some part of your end behavior should all be the same number. And if you have like asymptote at 5 and then other things at 4, like that doesn't make any sense. So that tells me you have no idea what you're doing, if that's what you give me. Alright, these questions are more in theory. When you look at a function, how can you tell if it's growth or decay? And notice function. I'm not saying the graph, the actual function. So it has to do with the base. If the base is greater than 1, you have a growth. But if the base is between 0 and 1, you have a decay. Now don't just tell me a fraction, because there's fractions that are bigger than 1, so you gotta be careful. So an example of a growth function would be like 3 to the x power, because the base here is a 3 greater than 1, so therefore it's growth. If I ask you to explain, I'm going to expect to see some words like that. Something like, the base is 3, which is greater than 1. And I might suggest you avoid using mathematical symbols in the explanation, simply because people often do that wrong. So watch out. Example of decay, how about 1/2 to the x power? So the base is 1/2, which is between 0 and 1. That's a gross writing. Alright, and then what if I get really sneaky and I say, what are your thoughts on these guys? Growth, decay, y? Well, here, 4 to the negative x power is really 4 to the negative 1 to the x power. So this is really a 1/4 to the x power. So the base here is really a 1/4. So that's actually decay, so we have to be careful about that. Here, the base 2/3 to the negative x power is really 3/2 to the x power, and 3/2 is greater than 1, so this one's really a growth. This was decay, growth, and then 1/5 to the negative x power would be 5 to the x power, which is also a growth, because now the base is 5, which is greater than 1. Alright, I think that's the end. Good luck on your summative.